All right. Okay, so the title that I gave you was an introduction to information-based complexity theory, which is a sort of long name. So I thought I would go over like an overview of what exactly this field is. So I'll talk first about goals of information-based complexity theory, and I'll just abbreviate it as IBCT since it's kind of long. So the first kind of overall goal would be, given a task, so given, I'll put a task in quotes here, we want to compute the minimal cost in finding an approximate solution. All right, so that would be kind of the first goal. And the second goal would be to actually find any algorithms which actually achieve that minimal cost. So I state these as goals. These are not necessarily things that have been done. They're things that would be nice. So like, especially the second one in particular, like ideally it would be nice if we could find the algorithms, but in most cases we haven't. So when I say task, the things that have been studied the most would just be like solving a linear system, AX equals B, and also finding eigenvalue, eigenvector pairs. And then something I'm working on is extending this to least squares problems. So you probably won't find much out there, but I've thought about that task a lot recently. Yes?
When you say cost, does that mean flops? Does that mean memory references?
Yeah, so cost will mean for us a matrix vector product. I'll define it more concretely too, but yeah, looking ahead, that's what we'll call cost. All right, so at this point, I can jump into some definitions, and there's quite a few to be able to understand all the statements. So let's start. So I guess first, I could skip this one. Do you all know what it means if a class of matrices is orthogonally invariant? I feel like anyone? No? I could write it down. All right, I'll just write it down just to be sure. So first, a class of matrices, we'll call it F, is orthogonally invariant if F consists of non-singular matrices such that for any A in F, for any matrix, and for any orthogonal matrix Q, we have Q transpose AQ is also in F. Okay. Examples of classes would be symmetric matrices. So if we take F to be the class of all symmetric matrices of the same size, positive definite matrices, any class of matrices defined by some property on their eigenvalues will also be orthogonally invariant. All right, so that's our first definition. So So we're going to talk specifically about this first task today, just solving linear systems. So we wish to find approximate solutions to ax equals b. So we have some rules that we're going to restrict ourselves to. So here are the rules. It's almost like we're setting up a game for ourselves, and then we're going to optimize what sort of solutions we can find within our own little game. Okay, so we know b. That's the first thing, so the vector on the right-hand side. For any vector z, we know a times z. Okay, so the idea is like there's a machine that can compute matrix vector products. So you give it a vector z, and it computes az. Okay, and then we also know that A is in a class of matrices F, and we know F. Okay, so so this second one is kind of the key of what I was saying, that we're calling cost a matrix vector product. And that's all we're going to be allowed to use is matrix vector products. And we're going to call that information. And so we're going to define something called an information operator. And the motivation behind an information operator is actually the Krylov subspaces. So that's what we'll jump into next. Okay, so I'm going to define the Krylov operator, which is related to the Krylov subspace. So for whatever reason, we usually call it nk instead of kk. On a matrix A and a vector B is just this set of vectors. So B, AB, A squared B, all the way through A to the KB. All right, so this is our Krylov operator. And we also want to define a general operator. So for a general operator, we'll call it IK, still dependent on a matrix A and a vector B. So this will be the set of vectors B, AZ1, AZ2, through AZK, where these ZI vectors are just real vectors of the appropriate size. So notice that the Krylov operator definition satisfies the general operator. So the Krylov operator is a general operator with the ZI vector just being A to the I minus 1 power times B. All right. Oh, yeah.
The notation with the brackets, does that mean that's a matrix with those as columns?
Yeah, you can.
Is that a span, or is it just a set of vectors?
Let's see here. It doesn't matter too much the way you think about it.
Okay.
Yeah. Okay. All right, any other questions? Okay, so to find x, we construct an algorithm, phi, which generates a sequence so we'll call the sequence xk. A sequence of vectors xk which converge to the true solution. So if you have seen iterative methods before, I'm just writing that down in words. So you have at each iteration, you find a new approximate solution, and hopefully each time you're getting closer and closer to the solution that you actually want. But then the key thing is here, at each step K, we can only use ik. I'll squeeze it in down here. So we can only use the set of vectors at the kth step. All right, make sense? Okay, so now we'll try to define what we mean by something being optimal under these set of rules. So first of all, the matrix index of an algorithm phi for a matrix A, we write as K phi IA, it's equal to the minimum of all K, such that the norm of A tilde xk minus b is less than or equal to epsilon for all A tilde, such that the information operator of A tilde is equal to A. All right, let me make sure I got that all right. All right. So again, we're calling this the matrix index, which has a long definition, but I'll explain to you what it means. The matrix index is just, think of it as the smallest number of steps to find an epsilon approximation to the solution that we're looking for. Okay, especially if you ignore this last piece. That's essentially what it's saying, right? We want to find the minimum xk such that we define an epsilon. I didn't put that part down, define some epsilon that you want. All right, and then we need this last piece such that these information operators are the same. And that's just because if you're given the information of A, remember it's just these vectors, you don't actually know which matrix you came from. Remember, that's kind of the game we're playing here. We just know these matrix vector products. We don't necessarily know the original matrix. So we're just saying this has to be true for any such A tilde where the information is the same. All right, so that's the matrix index. Again, the smallest number of steps to find an epsilon approximation. Okay, so then the class index of an algorithm phi for A, let's not say for A, just the class index for an algorithm phi, we define as K phi I F. So the notation just changes from, instead of a matrix A, a class F is just the max of all matrix indices for all matrices in our class. So it's essentially the smallest number of steps needed for the hardest problem in our class of matrices. That's how you can think about it. All right, so finally we'll see the word optimal. An algorithm phi is called optimal if the class index for that algorithm is equal to the minimum class index over all algorithms. And this has a special notation. It's called KIF, the optimal class index. All right, so this is our notion of an optimal algorithm. And we have one more kind of layer of optimality. Which would be optimal information. So information I is optimal if the optimal class index for I is equal to the minimal class index over all information. So we'll call it J. And this we denote as KF. So KF here is both minimizing over information and algorithm. So we're going 2 layers deep here. So at the beginning when I talked about like the goals of information-based complexity theory, I said, first of all, find like an optimal number, what did I say? How did I call it? The minimal cost of computing an approximate solution. So that's represented here. The matrix index is a minimal cost. So we would like to know that. And then the second goal was finding an optimal algorithm, which would actually achieve that. So here we're looking for the algorithm which satisfies this. And like I said, this is hard. It's not necessarily done. It would just be nice. All right, and then one more thing here. So we're talking about algorithms abstractly. The main algorithm I'll talk about today is MinRes. So let's just review what is MinRes. The MinRes algorithm I'll denote as phi MR for MinRes. At the kth step gives a vector xk, which is just C0b plus C1AB plus CK minus 1 A to the K minus 1 B, where the CI, C0, C1 through CK minus 1 are chosen to minimize the norm of AXK minus B. So that's the MinRes algorithm. All right, so that's basically all the background that we need to look at a theorem within information-based complexity theory. Any questions before I state the theorem? All right. So this theorem is from the 80s. It's really recent. Okay, so we'll have F as before, just an orthogonally invariant class of matrices. Pick an A in that class. Okay, fix some algorithm I, some algorithm phi, some information I, and a vector B with norm equal to 1. Then there exists an orthogonal matrix Q such that for B we'll define as Q transpose A Q. We have this result. So the matrix index for MinRes with the Krylov information, because that's what MinRes uses, on the matrix A is less than or equal to 2 times the matrix index for our algorithm phi with information I on this new matrix B. plus 2. All right, so I will explain what this means, but before I explain this statement, let me write down one more line, which I think is a little bit easier to understand. So also, the matrix index for MinRes with the Krylov information is less than or equal to 2 times kf plus 2. Okay, so this is another result from the same theorem. So let's talk about this statement first. So if you want to solve a linear system on my matrix A using MinRes, what does this say? What was kf? Is it still up here? So remember, kf was kind of that second layer of optimality. It was the most optimal number of steps that you could take over both information and algorithms. So this is saying, using MinRes on my matrix A, this is no worse than about 2 times as many as you could optimally need. That's the idea. Okay, and so this is a little bit weaker statement, but a little bit easier to prove. But it has the same idea. So if I want to solve my system of A using MinRes, it does no worse than some other matrix that I can cook up inside my class of matrices. So the question is this a good result? It seems like a little wonky, but I think it is a good result. If you consider that we're talking about some optimal algorithm and information that we don't even know, like we're just saying, okay, this supposed optimal algorithm and information, but we have MinRes and we have the Krylov information, so it's pretty good. All right, so I can give an abbreviated proof of this statement here, not the full proof. All right, so we start with a little bit of, we have to play around a little bit to set up our proof. So first, let the set E be the set of vectors f0, f1 through fn minus 1 be a full orthonormal basis for the Krylov subspaces for AB. And pick the first vector, f0, to be just the vector B. Okay, so I'm leaving a little bit out here. So you'd pick the largest linearly independent Krylov subspace and pick an orthonormal basis for that, and then extend, if needed, to a full set of size n minus 1. And again, pick the first vector to be B. And then just denote EJ to be the span of the first J of these. Okay, and then from here, this is kind of the setup. The rest of the proof is by induction, so I won't go through all the details, but I think I can give just enough that we can understand what's going on. So inductively, we're going to construct these spaces. So the first space is called G2, and it will be B, Z1, B1, Z1. Okay, so what are these? So first of all, remember Z1, Z2, Z3 were part of our definition of the information operator. So that's what this Z1 is. It's given since we have I. Okay, B1, you don't know exactly what that is yet, but I'll explain what it is in a moment. So G4 will be B, Z1, B1, Z1, Z2, B2, Z2. So again, Z1 and Z2 come from the definition of the information operator, and then these matrices B1 and B2, hold off for one moment and I'll tell you what those are. So we inductively construct these through G to M, which will be B, Z1, B1, Z1, Z2, B2, Z2, all the way through ZM, BM, ZM. Okay, and orthonormal bases. So we'll denote these vectors with G. So G0, G1, all the way through G to M. And again, let's pick the first vector to be B, just like we picked the first vector of our basis for the Krylov subspaces to be B. Okay, so now I'll explain what are these matrices BI. BI is equal to UI transpose A UI. So UI is an orthogonal matrix. So because of that, this matrix then is in our class of matrices F. And so BI is chosen, are chosen, so that the orthogonal matrix UI takes our our basis here, G2I, to this basis here, E2I. Okay, so what we're actually doing at each step of this induction, we're choosing an orthogonal matrix so that we can move back and forth between these two bases. And then from that orthogonal matrix, we're defining a new matrix, BI, which is in F. I'm skimming over a lot of details, but yes?
What is M? Oh, yeah, what is
M, so M is like my step in the induction. So, I mean, we can go to G to M plus 1. We just keep on going.
So does it stop at N?
It will stop. I'll have it stop at M, but I'll tell you when it will stop. We need to assume one more thing. So we have this, and also we need BM ZI is equal to BI ZI for all I, let's just say all I, for all I of the correct values. Okay, so this isn't too hard to believe. So remember, these matrices BM, BI are these orthogonal transformations here, and these ZI values are in these sets which we're defining a basis on. So the idea that we can have this happen, I don't think is too hard to believe. We have to pick carefully when we pick these matrices, but it's possible. Okay, so this is the induction, which we continue. The induction until the matrix index for our algorithm with information of some matrix BM is equal to M. So that's why it happened to stop at M here. So at each step, we're coming up with a new matrix. So, at KI, we're going to compare, or at step I, we're going to compare the matrix index of BI. And if it's equal to I, then we're going to stop the induction. And at that point, we go to the last step. So this is for some M. Okay, so at this point, let y be the mth iterate of our algorithm phi, and define now g2m plus 1 to just be g2m and put in y. So we had g2m, and we're just adding on one more vector. And also, we want to extend this basis now, so and extend. So we're going to take g0, g1 through g2m through g2m plus 1. And then we choose an orthogonal um plus 1 such that um plus 1 g2m plus 1 is equal to e2m plus 1. So this is what we had assumed at each step of the induction. We just are going one step further. And then finally define B to be um plus 1 transpose A um plus 1. So if you remember in the statement of the theorem, it talks about a matrix B. This is the matrix that we're looking for the finale of the theorem. Again, B is in our class F since um plus 1 is orthogonal. So it can be shown now that B zi is equal to bi zi, okay, which is, again, the equivalent statement of what we had before. This follows at each step by induction. I'm just not going through the details. So now we're going to see why we wanted this property. So why is this helpful, that B zi is equal to bi zi for all I? Well, consider the information operator at step M of the matrix B with vector B. So we have to think back a little bit of what I defined the information operator. So it was the vector B, and then the matrix B z1, and then B z2, all the way through B zm, since it's the information operator at M. So this was the definition. Now, because of, if we can show this, that means that this is equal to B, B1, Z1, B2, Z2, through BM, ZM. Okay, that follows from here. And then this now is equal to B, BM, Z1, BM, Z2, all the way through BM, ZM. And this follows from our induction, what we were verifying at each step, that we could go from B1, Z1 to essentially B anything Z1. And now this is equal to the information operator at step M of BM, B. Okay, so why is that helpful? Well, we said that for the algorithm on BM, it took M steps. So this is saying that the information operator for B and BM are identical all the way through M steps. So for the matrix B, our algorithm could not have found a solution sooner. And in fact, it should find a solution at step M as well, is what this is saying. So the matrix index for B is also equal to M. Right, make sense? Okay. All right, so we're almost there. Okay, so this means that our solution y will work for our matrix B. So essentially y gives us an approximation. So if we were looking for an epsilon approximation for our matrix B, y will do it for us. Okay, and B was equal to um plus 1 transpose A um plus 1. Right? All right, so now if we factor out um plus 1 transpose A um plus 1 y minus B, and essentially I want to take this out of the norm. Or maybe I'm going about, okay, instead of this, let's multiply in um plus 1. Okay, so why can I do this? Because um plus 1 is orthogonal. All right, so if I multiply this through here, we should just get um plus 1 y. And then here we'll get um plus 1 b. Now remember, um plus 1 is an orthogonal matrix, which we were defining so that we could move back and forth between bases, right? So b we defined to be the first vector in both of the bases that we were looking at. We specifically did that. So um plus 1 should take b exactly to b. So this should be um plus 1 y minus b. And now this vector here, um plus 1 y, is in E2m plus 1. All right, so E2m plus 1 was the Krylov subspace of dimension 2m plus 1. Okay, so what does this mean? So look, we found an epsilon approximation for the matrix A with the vector B in E2m plus 1. All right, so I might have just misspoken. This is the Krylov subspace. The Krylov subspace of dimension 2m plus 1 plus 1. So it's actually 1 greater, right? And that essentially does it. So this means that the matrix index for MinRes with the Krylov subspace for the vector A finds a solution in at least this many steps, 2m plus 1 plus 1, or 2m plus 2. And m was equal to the matrix index for that vector, or for that matrix B, excuse me. All right, so that was that first statement of the theorem. That was the outline version of the proof. So the essentially all that we missed was in detail each of the induction steps of how to accurately define all those matrices and bases. So any questions? Yep.
Why does B have to be unit length?
Okay, good question. It might not, except for that I left it out of all the earlier definitions, but in the general theory, they always take B to be of unit length. And if we're defining an orthonormal basis, yeah, that's the reason. But if it's not, you can just normalize, right?
Right. Well, I was thinking that it would be nice if we didn't have that restriction.
Sure. Yeah. All right, that's all.
All right, I'll cite the speaker.
Thanks.
Any further questions? I think a couple.
You had a couple?
I just have to remember, see if I can remember any of them. So toward the beginning, when you were talking about inductively constructing G2, G4, all the way to G2M, and you mentioned we need a few things. We need B sub I to be equal to U sub I transpose times A times U sub I. And there were conditions that U had to satisfy along with G. So U sub I times G2 sub I, or G sub 2I equals, yeah, exactly. And then also B sub M times Z sub Zi equals Bi Zi. So I got a little confused about which thing are we choosing, which thing are we constructing, and what are the things that we are, which things do we know to be true because we're constructing it to be that way, and which of those properties sort of follow? I get a little mixed up there.
Sure. Okay, so the first thing that we have to choose correctly is actually the set of the bases.
Okay.
Okay, so we have to, and it's actually, so it's a little bit confusing because I wrote G2, G4. We construct G1, G2, G3
Right.
along the way, but it doesn't become super helpful in the end. So we have to choose these correctly first of all. After that, then we choose the U. We already know at this point, we know this and we know this.
E is the Krylov subspace,
Yes.
so you know that.
Yep.
So you compute U by U is the orthogonal transformation that gives us. Okay.
Yep.
All right. So you construct U. So you construct G, and then you figure out U that gives us that.
Yep.
Subject to the constraint that U satisfies. U is orthogonal.
Yes,
Okay.
that's all.
And then you define B
Yes.
using that U. Okay.
Yep. And then this will follow.
Okay.
Yes.
All right. Cool.
That's good clarification.
All right. Thank you very much.
Sure.
Speaker again. That was awesome, Nicole.
Oh.
It's I feel like that's a rare